in Darmstadt, Jyväskylä in Japan. And he's also the winner of Alexander von Humboldt Foundation Award for Science. His recent interest is in climate change and the effect of climate change on marine life. So we'll hear also about this topic.
Yes.
And it's a pleasure to have you here, Giacomo. Please, the floor and the screen is yours.
So it's, well, many thanks for this very nice introduction. First I would like to start thanking all of you. For the Institute, Piotr, and all the Institute for the invitation, and all of you for being here. So the aim of my talk is a little bit to present the research we are doing in a laboratory which is situated in northern part of Italy. So as you see, this you see from my title. So I will speak, this concern is focused on nuclei, on nuclear structure. So I will speak what I've called here hidden symmetries. It's focused on astrophysics. In particular, concern reaction which involve the first generation star, and this is why I've called it stellar archaeology. And recently, as was said before, we have started a small research program which has been financed within the PNR, this recovery plan of the European Union, which is on climate changes and other paraphernalia. So let me come to this, what I mean for paraphernalia. This is a word which came into the Latin from Greek, and it is mainly, it has a very specific meaning, at least in Italian, which concern from the Roman Rite. It concerns let's say the real or property of a married woman, which can be brought into the marriage. So this can be as a doherty, but this is what is not the doherty. So it stays into the disposal of the married woman is called paraphernalia. But in the last century, it took another meaning, especially in the English-speaking world. And so it took a meaning of gear, tackle, outfit, equipment, and this is the way I'm using, the meaning I'm using in this talk. Okay, what I will speak about. So I've selected some topics which one concern one of the basic symmetry of the nuclei. Nuclei can be spherical, prolate, oblate. One of the shape is triaxial. So I will speak about rotation of triaxial system for two reasons. First, because this is very strongly linked to basic forces. It comes directly for the pion exchange. But also because what you expect from a quantal description and from the classical description, the expectations are diverging. Then I want to speak about one of the oldest symmetry of the nuclear physics of the shell model, which is called seniority. And in particular, the link between seniority and particle Hall conjugation, and a phenomenon which is known in quantum mechanics, which is called the Berry phase. And in particular, the seniority, I will show it is a nice example in nuclear physics of the Berry phase. And then I will not speak about isospin phase, there will be no time. We have done some experiments basically related to the future perspective of the laboratory, so the availability of radioactive ion beam for studying reaction which power the star, and we have in particular performed with the solenoidal spectrometer. And then I will conclude showing this application that we have just started. We are I'm going to Spain after this visit to Krakowie for the measurement concerning this isotope for climate change, where we try to look to the adaptation of marine species to the new climatic conditions using the methods of the nuclear physics. So then first, now a few words about myself. I'm working in a laboratory, which is the Legnaro laboratory, located in the town, in northern part of Italy, in the town of Padua, which is the second oldest university in the world, and the first one which provided the degree for a lady, in the 16th century, which is located something like 30 kilometers from the town of Venice, which is a town which is particularly affected by the change of the climate. This is a picture that I took a couple of 3-4 years ago after a very high tide. You see one of the evaporator, we just ended on the shore. This is actually not happening anymore, fortunately, due to technology. And you see this is here, due to technology. I don't know why. Yeah. Yes, due to technology. This is, you see, this is called MOSE because it's cutting the sea. It is an electromechanical barrier which is raised in the cases of particularly high tide, and so it's preventing that the town is flooded by the sea. So it's an accelerator-based laboratory hosting several accelerators. The largest is a linear accelerator based on superconductive technologies. So it's using superconductive cavities to accelerate all ions from protons to uranium in order to overcome, to get energy to overcome the repulsion among, the ions themselves. And so you create radioactivity. You can, the reaction I will focus are multinuclear transfer reaction, which are actually something which has been pioneered by this institute in the past, and we are using now regularly, let's say, to focus on nuclei which are on the neutral-rich side of the nuclear chart. So, which is now the detector we are using? This is called Agatha. It's a kind of new generation gamma ray detector. So we measure the excitation of a nuclei detecting the gamma rays emitted in the transition between excited states. This is the result of an international collaboration, and Poland is a part of it, 13 countries, with unprecedented performances, which are listed here. In efficiency, kind of the capability of selecting a small signal from the background and identifying the direction of the incoming gamma rays. All this is achieved through the gamma ray tracking. So reconstructing the history of the gamma ray inside the crystal. And this is performed combining very high segmentation. So they are germanium crystal, very high segmented, 36-fold segmented, which are then combined with the digital electronics in order to compare, let's say, the direct signal obtained by the segment where the ionization is happening with all the neighboring one where the signal is induced. And from this comparison, which is called signal decomposition, you get the identification of all the interaction points, so the points in which the gamma rays are interacting with the crystal. And you know the points with the precision of 5 millimeters, you know the energy in each point, and then you apply the Compton scattering formula, so you reconstruct the history of the gamma rays inside the crystal. And all this translates in what? In very high performances. This is, I was saying before, the nuclei can have different shapes, like spherical, oblate, prolate, and very elongated, like super deformed, hyper deformed. Just I want to remember, this is an article written from the people here searching from hyperdeformation. So this is a simulation in which is compared the performance of the best, let's say, array of a previous generation with the present one, and you see there is a gain factor of 300, therefore an high discovery potential. This the physics campaign, this is international, the result of international collaboration. So it's a moving device going from different laboratories. So it started in 2010 in Legnaro, and we got the interest from the Italian Post to get, which they dedicated the stamp to the first 5 cluster of this detector. Then it moved to Germany, 2012, to France in 2015. And now it's back to Italy, 2022, and we stay at least until 2026. Meanwhile, it is grown, covering a larger solid angle. This is how it looks like. So it is this one, combined with a spectrometer, which provide, with the aim of providing a full identification of the reaction product. This is just to show the experimental campaign. You don't need to read all the experiments which have been presented and performed. I mean, we run one experiment after the other. But just I want to show that it concerns, I mean, it covers basically all the nuclei, I mean, the nuclear charge, going from both from the neutron deficient side and the neutron rich side. And in particular, you see, these are the different, the allocation of beam time of the different scientific committees. Just I want to, most of the experiments are involved, I mean, are involving a new nuclei on the neutron rich side, because, I mean, this is because we are using this reaction mechanism which allow to move, I mean, to populate nuclei which are, let's say, slightly or neutron rich. And there is many reasons, I mean, from nuclear structure to nuclear astrophysics, they are involved, I mean, the neutron rich side of nuclear chart is the one which is mainly involved in the process of nucleosynthesis or explosive nucleosynthesis. How this is, so this is how this proceed. This is, we use, I mean, you make use of the fact that of the massive transfer between a neutron-rich projectile and the neutron-rich target. And in order to populate hundreds of nuclei around the projectile, this is an example, is a reaction like selenium on platinum. And there are up to 20 neutrons transferred. And so provided that you can identify one by one the reaction channel, then you get the information, the spectroscopic information of each one of these nuclei. As I said, this is a mechanism which has been studied in vast and especially developed from the people from this institute. This we do with a spectrometer, which on the basis of the position and time at the entrance of the spectrometer, position, time, and energy at the focal plane of the spectrometer. And this is same, I mean, the result of the reaction I was showing before, selenium on lead, in which you see these are the different Z, I mean, from that are populated, and you see the mass distribution. So all the masses are very nice separated. So you can simply gate on one of this channel and get the spectroscopic information as it is shown here. So this is for the same. You see, this is the population of the nuclei, I mean, by nucleon transfer. Then you have the gamma rays as a function of the mass, and you gate on the mass, and you get the spectra where you can identify, in this case, osmium nuclei. So let me say, you can also use, I mean, of course, the reaction is driven by the energetic of the reaction, and you can use different combination, I mean, of different Q-value combination in order to make either proton stripping, I mean, to drive the transfer towards the wanted region using either proton stripping and neutron pickup channels or proton pickup and neutron stripping channels. And all this, I mean, the probability to populate such nuclei are sizable and can be predicted. These are calculations, I mean, these are semi-classical calculations in which one can predict, I mean, the probability, the cross sections involved, and also you can see the difference, for example, in order, I mean, choosing, for example, a neutron rich projectile respect to neutron deficient projectile. You see that this distribution is shifted much more towards the neutron rich side of the nuclear chart. So all this, for example, it is meant for studying nuclei which, as I said before, are not easily reachable with other reaction mechanisms, simply because there are no stable targets around. And so this is, for example, the one around the N = 126 shell closure, I mean, which is important for many reasons, but one of the reasons is also because it is related to one of the peak in the isotopic solar abundances. And but I will, what I want to underline here is that since we are dealing here with a change, I mean, shape of nuclei going from very deformed to spherical, then passing by triaxial deformation, which is one of the cases I wanted to mention. So why this is important? Well, first of all, because very strongly linked to the particle physics. you see, because it's the direct consequence of one pion exchange, which makes an interaction which is not isotropic, it's tensor, and naturally the tensor interaction produces nuclei which are triaxial. Now, the other reason is because there are, at least for me, there are different predictions in a quantal description and a classical description. If I take the rotation of triaxial system in a classical description, then you don't need to read, but simply in order to, this can be described considering the conservation of energy and momentum. And this is, one is a sphere, the other is an ellipsoid, and the intersection are basically two points or two loci. And therefore, the rotation is unstable, at least the rotation around the intermediate axis, which is instead the main axis of rotation, the one which is preferred in the case of in the quantal description. And this brings me, if you allow, to a small digression. So we move, I move to 1985 in February. There was, you see, it was the Soviet Union. It was just at the end of the Soviet Union. There was still the Salyut 7 was the space station of the Soviet Union, and the signal with the Soviet Union was lost. So the station began to drift, and all the systems were shut down. And fortunately, at that time, there was no astronauts in the station, and therefore they had, in principle, there was no problem. The astronauts here, they had left just, and this happened before the new crew was arrived. Anyway, it was decided to repair the station, so 2 astronauts were sent to the station where nothing, no biological system was working. They were Vladimir Sadnikov and Viktor Savink. And they, on the space mission Salyut 13, and all this, has been seen, in order to repair in a station where everything was shut down, and this has been has been defined as one of the most impressive feats of in-space repair in history, and has been also the basis of a movie, a Russian movie, 2017, Salyut 7. Now, here, you can see, let's see. They observed repairing this. You see a screw. This is just a triaxial object, which is rotating in microgravity. And you see that it's just changing direction, switching from one side rotation to the other. So this effect was considered to be new, and it was given the name, you see, to the astronaut which had found it, was kept secret for a while, and then it was published in Springer Link, as you find, and under the twisting tennis racket, because this is just a tennis racket, this is a triaxial object. Then if you just make it rotating this way, then it always returns also, because of this instability which is present in the classical physics. And this, as it is written in this, you see, the twisting phenomenon seems to be new. It is not mentioned in the recent article on the Eulerian wobble, in general text on classical mechanics, or in specialized text on rigid body motion. Unfortunately, or fortunately, this was not true. In reality, it was known. You see, it was, you find in the rotation of corpse of Louis, of a French mathematician, Louis Poinsot. It is the name of, his name is written in the first level of the Eiffel Tower, among the people which have contributed to the knowledge of that. And he described, just as I was telling, you see, this is the intersection of the ellipsoid for the conservation of angular momentum and energy. And then you get only 2 points of stability that makes this oscillation. If you look on the web, you will find also that other people which have thought that this could have been a reason for the changing of direction of the magnetic field of the Earth, because the Earth is also triaxial. So in principle, they suggested this solution. Now, of course, one knows very well the axis of rotation through the satellites of the Earth. It is triaxial, but it's not rotating around the intermediate axis. It's rotating, as all satellites do, it's rotating around the shortest axis, the one that is maximized the moment of inertia, as all the satellites. And in principle, if you have some dissipative element forces, like, for example, the interior of the Earth, this is the most preferred rotation because, I mean, the other is unstable. And there is only one case where this happens, and this is a moon of Nix, a satellite of Pluto, much smaller and probably solid. This is why it happens, in which, let's see, yeah, which this is a reconstruction obtained using the data of the Hubble telescope, in which it's just switching from one direction to the other. But all the other satellites, they don't do this. So let me now move to the quantal description. This is, you see, in a quantal description, you instead, I mean, normally you use parameters for describing the shape, like in this case, epsilon and gamma, and the triaxiality is described by a gamma with a value equal to -30 in this. One can calculate which nuclei they are involved, they show this shape. I mean, at the moment, there is the idea, this is much more general than in reality it was thought in the past. Before this kind of deformation was thought to be something very rare. In reality, at the moment, I mean, they are recalculated, theoreticians are recalculating on shape because of this relation with the basic property of the pion exchange. Anyway, here there is a way of calculating the stable shape, minimizing the energy as a function of the 2 degrees of deformation. This is the minimum corresponding to triaxiality. And then this is one of the cases we show this kind of behavior. Then you see, rotation around the triaxial axis in the low energy part of the nucleus. And then as soon as you break a pair, in this case a proton-neutron pair, then you move in a minimum which corresponds to a rotation around the shortest axis. So the prolet deformation, which is also represented here in this diagram for the different. So this can be investigated. We have tried to investigate this, and this you can do looking to the lifetime of the states. In principle, the electromagnetic transition matrix elements. So the transition which provide the numbers which provide the probability for which a level they excite in another one. So what you do, you measure the lifetime of the states. You use the Doppler effect, the same like in the sounds. I mean, but for the gamma rays. So each gamma ray is split in two because you make the emission of the light, the emission of the gamma rays by the nuclei flying at different velocity, and then from this you can obtain the lifetime of the states. This is called a plunger, and then you combine with the spectrometer, so you have selectivity on this. This is just showing the results. So you have you can determine, I mean, this transition probability one by one along the excitation of another system which shows triaxiality in the ground state, and the behavior is just very, very according to what I was showing before, the prediction concerning, I mean, this changing of axis of rotation. So the whole nucleus seems to change from the ground state, rotating around the intermediate axis to the shortest axis in the excited states. So, and with this, and from this, I would move to the second example I want to show, which is another symmetry, let's say, which is one of the oldest of description of nuclei. It is called seniority. Actually, it's a name which was given by Racah in Florence. It was related to the number of how many, it was related to electron states, and it was representing the number of pair of electrons which were broken. So similar, this has been taken in nuclear physics, so it represents the number of pairs of nucleons which are broken. So it is, now the conservation, this is conserved in the nuclear system, at least this conservation of seniority, so the number of pairs which are broken, which are not coupled to L equals 0, they introduce some conservation law. So one conservation law is the fact that 2 plus energy is independent of the filling of the shell. So when you move from one nucleus to the other, the 2 plus energy is always the same energy. Then you have some conservation law concerning other observable. So for example, odd tensor, they are diagonal in seniority. And this explains why seniority is also conserved in nuclear physics, because the delta interaction, which is a good representation of a strong force, is an odd tensor, and therefore this is diagonal in seniority. Therefore this is conserved. Even tensor, no? Instead they go to 0 in the middle of the shell. And the transition, what I was showing before, the transition matrix element, the probability of the excited state to the other, it is an even tensor, and therefore you see it shows this kind of behavior. It is a parabolic behavior. So if you change inside the same seniority multiplet, you find a behavior like this. It goes to 0 in the middle of the shell, and within changing seniority from 2 plus to 0 plus, it shows this parabolic behavior. So all this is naturally happening up to a certain shell of nuclei. It is the G9 alpha in case, before, just by counting, let's say. But there is no evident reason why this should happen for a heavier system. And this is why what we have tried to investigate. And what normally was observed in the past is that you even if there is no special reason why this should be conserved, then you always find some states which they never mix. And so this is kind of a sign of a symmetry which is lying behind. So what we did was going to look to different this kind of behavior. So seniority multiplet in different shells for proton and neutron. So Z equal 28 and N equal 50. So this and N equal 50. So the first experiment I'm showing was done in France in the previous campaign of Agatha, using similar setup, only another spectrometer, but exactly the same setup I was showing before. This is in Ganil, in France. The plunger experiment, so lifetime experiments. And here, what I'm showing is just these 2 peaks which represent the emission at different velocity, from which you determine the lifetime of the states. So you do all the analysis of the data, and you find, you see, a very nice example, textbook example of seniority conservation, what I was showing before. 2 plus energy are independent, you see, of the filling. So you go from one nucleus to the other in the same multiplet, and you find they are almost all the same energy. And then you have the transition matrix element, the B2, which shows either a parabolic behavior or an inverted parabola with going to 0 in the middle of the shell. So this is for the N equal 50. Then we went to Z equal 28, nickel isotopes. This is much more exotic system that cannot be reached in the way I was showing before. So we had to go to one of the most, let's say, at the moment, one of the most powerful laboratory for this kind of physics in the world, which is in Japan, is in Riken, doing a kind of very amusing experiment, because we did 2 experiments with the same beam time. Because we were doing Coulomb excitation, so exciting gamma ray, exciting nuclei going, by electromagnetic interaction, and implanting into and studying the decay afterwards. So what we were doing was using uranium fission on a beryllium target. Then the recoil nuclei were separated using a spectrometer which is called big rips by electromagnetic separation. Then identified, then Coulomb excited on a light target, and then again identified, and then implanted into the focal plane, studying the decay, the beta decay. And we looked to some of these neutron-rich nickel isotopes. At the end, again, we found the same behavior, very nice, according to seniority conservation. There are differences, but they are related because there are different nuclear regions in which interaction are different. But nevertheless, I mean, so the order is not the same, but for the rest, everything was according to the conservation of seniority. Interestingly, there were, you see, again, a set of states, like in this 4 and 6, of seniority 2 and seniority 4 that were not mixing. So even though, as I said, for these shells, there is no reason why they should not mix. What you can do next? You can go in the middle of the shell, where the seniority, where the symmetry is fully respected. So and this corresponds to nickel 73. So which is, I mean, looking to the filling of the shell, it's either a particle or you can see as a 5-particle nucleus or as a 5-hole nucleus. I mean, it has in the middle of the shell. And for this, and this is what we got. Unfortunately, this is a low-resolution spectroscopy. This was done with scintillators. But nevertheless, you see a decay which is very different in the middle of the shell from the other side. And again, you find 2 levels, 5+ in this case, seniority 3 and seniority 5, which not mix. Then we went to, and we can look for another case. And this is a 2 G9 shell. So again, heavier nuclei, led to 213, is again a 5-particle, 5-hole nucleus. It can be described either as a 5-particle or 5-hole nucleus. This is lying in the middle, you see, of the 2 G9 shell. Also, this was performed using induced fission. So you have a uranium beam, which is just going on beryllium target. Then it is then the fission is fissioning. The fission fragments they are then analyzed and then implanted in the focal plane. Then you study the beta decay. So the result of all this was again this parabolic behavior. Now I have not time to go into the detail, but you see, this was the experiments. I say it was very nice, kind of again a textbook example of seniority conservation. But in order to get it compared with theory, it was necessary to introduce 3 body forces. So it's an example in which you need 3 body forces. But this for the even systems. Then if concerning the middle of the shell, 213 lead, this was the result. So it was kind of, you see, the decay was divided in 2 main branches, 20%, 80%, which could be very nicely described in terms of the shell model. So you have the ground state, which is seniority 1. Then you have the excited states, which can be either seniority 3 and seniority 5. And again, here you have very close levels with same spin, which they don't interact each other. So you see, 2 close lying 17.5+, which do not mix. So this behavior we found everywhere the same way. We could reach. Now, again, is a 5-particle nucleus or a 5-hole nucleus. So that means that this nucleus can be seen as a loop in the particle-hole symmetry. See, it can be seen as a loop in the particle-hole symmetry. So a cycle resulting from the geometrical properties of the parameter space of the Hamiltonian. Now, if I take this definition and I look what it is, this is the definition of a phase. This is a Berry phase, it's called, which was introduced by Kato in 1950, Pancharatma in 1956, Higgins in 1958, and Berry gave it the name in 1984 and also popularized it. And it's present almost everywhere in many aspects of physics, from optics, condensed matter, quantum electrodynamics. The case I like more, and is also the more simple, let's say, is the Foucault pendulum. So the Foucault pendulum, I mean, of course, it showed first directly the rotation of the Earth. But if you look, see, in here, what you see, I take, see, if you make this is the Earth, you make a transport of a vector, a parallel transport of a vector, and then you make a loop and come back to the pole, then you see that the vector just comes with a phase shift. And this phase is what is a Berry phase. In other words, the mismatch angle of the Foucault pendulum follows from 2 ingredients. The parallel transport along a longitude that is due to the adiabatic rotation of the Earth, but also it incorporates the information about the curvature of the surface. So if the Earth would be cylindrical, there would be no changing of the plane of the pendulum. And this phase can be calculated just normally, as this was you see like the integral of 1 over the radius of curvature of the Earth, this is sphere. If you do it, you find just the mismatch angle of the Foucault pendulum normally known. This, of course, can be generalized to many interactions, many Hamiltonian. It's much more general, meaning, of course, it has many other aspects of the Earth. One is the topology of planetary waves. I mean, of course, you have both oscillation of the atmosphere, but also of the oceans. In particular, you have the Kelvin and Yanai waves, and they make this each kind of loops, especially going around the equator. And so they got different phases crossing the equator, and this is considered, they are considered, this is across the Pacific, the precursor of the Niño effect, for example. Coming back to nuclear physics. So we have now a loop between in the particle all symmetry plane. We apply this calculation of the Berry phase, as I was saying. This can be generalized to any. See, one can define a Berry curvature and then calculate the phase shift as a function of the Berry curvature, and then this can be translated in the language of nuclear physics. And then you see the matrix element, this transition matrix element, they get a phase here, which is related to change in seniority. And you see the different, the matrix element is different from 0 only if this seniority change is at minimum equal to 4. So, and now if I come back to what I was showing, to the level scheme, you see it here. So the only states that here can mix are the seniority 1 and seniority 5. The difference is seniority 4. But the other states, seniority 3 and seniority 5, they can never mix because of this effect of the Berry phase. And so this is some way embedded in what we observe normally. I mean, I think a nice example of the Berry phase in our field of physics. Okay, let me now come to a different topic which concerns the future development of the laboratory where I'm working, which is the production of radioactive ion beam. There is a project, unfortunately now very delayed, which for producing radioactive ion beam using an isol source, using induced fission of uranium. So in few years from now, there will be radioactive ion beam. We are trying to use to make radioactive beam using producing the coupling, let's say the production stage and the acceleration stage. So producing radioactivity, for example, with the cyclotron, and reaccelerating directly for the moment into the present linear accelerator. All this, we are testing this possibility. This is the cyclotron which has been bought. It's a commercial one, 70 MeV proton, 500 nanoampere in intensity, and which has started the operation. Which is operating now. And this one can use, for example, for investigating nuclear astrophysics, in particular the reactions which are involved in the element formation in the explosive nucleosynthesis. And yeah, just to say that every element of nucleosynthesis even the air process site is not very well known. It is now we know after the observation in 2017 of the coalescence of a neutron star that the neutron star merger are indeed the site for the nucleosynthesis of heavy elements, but supernova can only be a case, a site, an astrophysical site. This involves many reactions to be measured. Here, this is of course, the nuclei which are involved are very far from stability, and they can and they are out of reach for most of the facility at the moment, but one can use models and then can kind of test the models in more in nuclei which are more achievable. And this is what we have tried to do, in particular for this process nucleosynthesis. So they are neutron capture reactions, which are that you want to measure in order, to explain, to describe the element formation in the universe. One of the points which is of interest is, for example, in this case, the Krypton 85 system. This is because there are nuclei which they have an isomer, and the isomer in a stellar environment can be populated, and this is therefore changing the effective lifetime, and depending on the neutron flux and on the temperature of the star. And so from measuring all the elements together, you can reconstruct the temperature and the size of the star. This we have investigated using, and this was kind of the novelty, a solenoidal spectrometer, which there are nowadays two available, and one is a FRIB. One of we would have the intention to build also one in Legnaro. The interest is because it provides a very high definition of the energy, both for the light particles, in this case, in inverse kinematics, and especially if you combine with gamma rays. This just shows, you see, that the comparison of the particle resolution in case of inverse kinematics, and how this is resolved by using solenoidal spectrometer. So we did an experiment in argon. This one, Krypton 85 dp gamma, using an indirect method, and this is a radioactive nucleus, so we provide the activity and we put it into the accelerator, and combined with the gamma rays inside the solenoidal spectrometer. And at the end, everything worked very nicely, actually. This is the spectrum that you observe, the different excited states, in this case of Krypton 86, until you reach to the particle emission. And then you combine this with the information about the gamma rays. You see, this is the particle emission threshold. And you have above, of course, you go to particle emission, and below you see the excited states of the nucleus 86 krypton. And from this you can determine, using the method, this is the surrogate reaction method is called, you can determine the neutron capture probability, the cross-section. There are many cases that can be investigated this way. Another one which we got approved, in argon in this case, is concerned the explosive nucleosynthesis, the supernova, and iron 50 is an indicator of the supernova, of nucleosynthesis of supernova, because it's a lifetime which is long but shorter than the lifetime of the Earth. So it is an indicator of the fact that the nucleosynthesis is happening continuously. Of course, there is the interest in trying to understand the reaction which produce and destroy iron 60, and one of these is the 59 iron N gamma, which is the purpose of this, if we will succeed to do, because also 59 iron is also radioactive. It is a much shorter lifetime. It has been produced in one of the, in a reactor, and then separated and then accelerated. This is in argon. And with this, I move to the last topic that I want to show. So which is what I call which concerns climate change. So we did the recovery plan of European. We got financed, actually two projects, one in Spain and one in Italy, which addresses, with intention to address the adaptation of marine species to projected climatic conditions. So, of course, the amount of carbon dioxide in the atmosphere dissolve into the water, fortunately, because otherwise the effect would be much more. and this changed the chemistry of the water. And this change, of course, has an impact on all the species which live, especially the one that built exoskeleton of calcium. So this, of course, comes from many in the cycle, partly natural, partly from our impact on the composition of the atmosphere. And as I say, the part of CO2 is dissolving into the water, making the water more acid. This is just, you see, the Milankovitch cycle over the last, hundreds, 100,000 years, and which shows actually the increase of CO2 concentration in the last period. Even, the Earth, of course, has had a period even not very, very long ago, where the concentration was much higher, but always with impact on the living species. Now, and this makes as an effect. This makes ocean acidification. And why? Because the CO2 dissolves into the water, creating carbonic acid. Now, the carbonic acid reduces the pH of the ocean. But this is not the only effect. It also binds with the carbonate ions, which are dissolved into the water. And the ions are making bicarbonate ions, and these are the ions which are used by shells, for example, to build the shells, the exoskeleton, by corals to build the exoskeleton. So there are less carbonate ions available for building the shells and corals and all what is concerned this kind of biological of the biology of the water. This has many effects. Of course, it's effect on the plankton, and all the chain which is related to plankton up to availability of food for human beings. And so this is we got the interest in some sense of Valencia community because of the fishery, so the effect on the fishery, and also we got the interest from the Oceanographic, which is the largest aquarium in Europe, because they are interested in find a way of making the coral surviving. Interesting going into this topic, I realized that really experts, they consider that already 1.5 degree increase of temperature will make disappearing all the corals. And so, the only solution that they see, at the moment we expect 3 degree, not 1.5. And so we got this. You see, this was in the was financed within the Valencia community with the interest in corals from the point of view of the oceanographic, and in let's say mussels for the Valencia from the community of Valencia. So how do we want to do? How are we trying to do? We are trying to do using to monitor the growth of these animals using radioactivity. So, of course, you need something which is incorporated into the exoskeleton. So calcium 45 or calcium 41. So we have started the calcium 45 in Spain. This is because, it is, in principle, is something which diluted you can use in Spain outside a kind of radioactive controlled institution. So, for example, in aquarium. So we, unfortunately, since by the time we got it approved and we started, before calcium 45 was very easy to buy, then we couldn't find it anymore. So there was no way to find the calcium 45 anymore, so we had to make it. So Grenoble offered to make an irradiation, so we made the calcium 44 irradiated in Grenoble. They don't make an irradiation only for you, for us. They made an irradiation for several people, so we got gigabecquerel of calcium 45 that no one of this laboratory where we were involved could receive because it was too high radioactive quantity. So we had to go to PSI in Zurich to make it just dividing in pieces, in smaller pieces. Then we went to Madrid for the chemical separation. And now, just 2 weeks ago, this arrived chemical separated in Valencia. And now it is put into the water and the animals are just already there and so on. In Italy, unfortunately, or fortunately, I don't know, the rules are more strict. So the limitation of using radioactivity is 2 orders of magnitude lower than in Spain. So we couldn't use this one. And so we went to this one, calcium-41, which is the advantage of this one, is that you can measure directly the activity. You measure the electrons. Anyway, there are 100 kV electrons, but you can measure the electrons. Now, and this makes a huge improvement. You don't need to kill the animal. I mean, just you measure, I mean, at least you try, because in principle you can put, as I will show later on how we try to measure, you can protect and put into a scintillator. This one you have to do mass measurement. There is no other way. But at least use something which is not existing on the Earth. So if you find an atom of calcium-41, this comes from your, from what you have, is your tracer. So what is the intention is how do we do is you see we put in a container, I mean the water which is rich in calcium-45, and this is distributed in different aquaria. One with the Mediterranean mollusks, in which we have you see the present pH and simulated pH, which is just bubbling CO2, I mean CO2 carbon dioxide into the water. And the same we do with corals, much more difficult because normally they are much more delicate. I mean, they don't survive easily. And then when you take out of the water, they can survive only a few minutes. So this is still ongoing. This is, for example, where they grow. This is in the Oceanographic of Valencia, where they grow the corals. See, and here they survive. Then they take some. We have a person there which has been, which is take care of this. Which take a piece of the corals and they put into this basket where in another one this has been diluted the carbon-45, the calcium-45. Since we don't, I mean, since we cannot have a continuous flux because otherwise we would need too much carbon-45, only a part of the water is interchanged, 10% is changed every week, and it's just thrown away, and the other is replaced. So this is the way it is measured, but this has still to start. There are different attempts, just using a liquid scintillator, eventually with an anti-Compton shield to reduce the background from outside, and then putting some protection for protecting the animal from the liquid scintillator. This still, as I said, is still ongoing. One of the main problem that at least I would expect is the fact that the auto-absorption of the electrons from the exoskeleton, which will make quantitative measurement quite difficult, but this we will see. Meanwhile, this was the signing of the agreement during the COVID, this was, in the Oceanographic of Valencia. Meanwhile, a year later, we got approved another project in Italy. This is with the Marine Institute of the University of Padua, which is located in a town that is in the south of the lagoon, Venice Lagoon, which is Chioggia. This is the institute, very nice. You see, this is from a meeting that we had here. This is what you see from the window. It is difficult to believe, but there is a coral reef also in the Adriatic, which is called Tengu because this is in the local way of speaking. This was, you see, the fisher, they found that the nets were hanging on the bottom. And this is what it is, something which is skipping. This is the meaning of this term here. And so with this, you see, there is the interest, and so this is the same basically, only that is using calcium-41. It's only because we couldn't use calcium-45. Even calcium-41 was a history to find the agreement of the radio protection of the University of Padua. It's focused, you see, at this kind of mollusk, same as having controlled acidification. The difference that we are also trying to do here is, you see, there is a place in, maybe others, but the one that I know, in nature, where this changing of acidification are natural, and this is close to volcanoes. And if you go to the island of Ischia, which is in front of Naples, this is one of the largest volcanoes of the world. It's what is called the burning fields, i Campi Flegrei. And this is what you see if you go underwater in this region here, you see this is the island, and this is there is a castle, Aragonese castle here, and you see that the degree of acidification, you see this is the pH, is changing continuously from, let's say, 8.1, which is here, to even 6.9, which is what is expected in hundreds of years from now. And so what the biologists are doing are going there, and then they take samples, elements which are growing there, and so they are growing in different conditions of acidification, and then they brought to Chioggia, and they do this kind of measurement. See also this kind of, they try to have animals which are relatively frequent. And saying like this, I will conclude. I thank you for the attention. And as I said, going back to this entering, for me, that I am not an expert at all in this kind of topic, I've realized that experts, they consider that already 1.5 degree of temperature will make basically disappearing all the large variety of coral existing, and so the only solution at the moment that they present is to try to move most of them in some protected area, which is one of these is the Gulf of Aqaba, so where microcosms are existing. And so thank you very much for the attention.
Thank you very much for this exciting lecture, Giacomo. Discussion, questions? Piotr.
So you covered so many subjects, but let me ask concerning the first one, this Janibekov effect. If it exists in nuclei, what signature in gamma spectrum would you say?
No, I have not understood.
If this Janibekov effect in nuclei took place, what signature in gamma spectrum
in gamma
would
spectrum,
you expect?
it is the one that I show in the sense that this oscillation from one to the other in quantum physics doesn't exist because it's a stable solution. It's a stable solution. So it is induced by the breaking of a pair, the changing of axis of rotation.
It was actually also my comment and question, because I do not quite agree with you, because we know in nuclear physics effects related to triaxiality and somehow maybe related to this Russian effect. We know two things at very high spins. One is the wobbling, nuclear wobbling, which we observed the rotational bands, and then the decay changes from one rotational band with one moment of inertia to the another and goes back and forth. This is called wobbling. It was discovered, we had first experiments in Riso in Denmark, then it was followed up by other experiments with Euroball. This is one thing, and the other feature is the chiral bands, which was when you have the triaxial nucleon and then one that is. No, and so I don't know if this is exactly this.
All this exists.
My question was on top of this comment is whether do you foresee the continuation of such experiments with Agata, because this is for high spins. This is the device which would be ideal for that.
So all the, of course, first of all the chirality exists. I mean, there is a phenomenology of triaxial nuclei. I didn't want to say that this doesn't exist. I just want to say that at least in the low energy, in classical mechanics, you have instabilities of a triaxial object, which is not in nuclear physics, I mean, in quantum description. Then if you go to high spin, and you have several, you have wobbling, you have all this, but this is not exactly, I mean, this is not what was, I don't think it exists an effect which is called Janibekov. This just came as a web, as a kind of a misinterpretation. Then, of course, there is a large variety of phenomena, very, very interesting, by the way, in which, I mean, they concern triaxiality. and this is actually, I mean, now I didn't go into details, but you see that the B2 are going down, I mean, which is kind of representation of a lining of single particle states there. I mean, there is always, but at least to my understanding, this is not what is called the Jannetnikov effect. This I wanted to say. Now, concerning Agatha, yes, I mean, there is a new campaign. I mean, there should be a new campaign, where normally you do fusion evaporation to reach a high spin. And this is supposed to be after the campaign, the present campaign. When this will happen, well, it's not fully decided. There is a meeting of the whole community, I think, in October, and this will be decided by the community of Agatha when this will happen. Concerning the laboratory, let me say that everything has been done in order to be prepared to, I mean, this requires a completely disassembling and reassembling of the present setup of Agatha. And this has been, it has been done. It is designed. So it can start, it will start anyway, I mean. So, but the moment, I mean, the date, this will be decided by community. And so I don't know. We thought we had a plan before, but now, I mean, this is just postponed to the decision of the research community of Agatha, which will meet, I think, in September or October. I don't remember exactly.
Do we have more questions?
How long will Agatha stay in Legnaro?
The moment is until 2026 for sure. If this will be prolonged to 2027, this will be decided after this meeting of the community.
And this problem with reef, climate exchange reef is very, very important, but I think much more important is the temperature, which...
They are related. They are related quantities.
Sorry?
They are related quantities. In principle, you can determine one by the other. Temperature and acidification, they are strictly related. You can go back also in the past. Because this is a possibility which gives this kind of, I mean, of isotopic analysis. Because, for example, from the boron nuclei, I mean, boron 10, boron 11, they all stay in an equilibrium, which is linked to acidity in the seawater and to the temperature. So they are strictly linked.
Last one more.
So concerning this picture that is on the screen, so why this Gulf of Aqaba should be preserved? I mean, there is kind of specific feature, or I mean, this acidity
why
does
why
not change,
this is a good place, I don't know. But this is there is a kind of a, I don't know, project, international project. I've heard that it is meant that this is a good place where I suppose because there is a microclimate where it is, but this is I don't know. It exists.
Then how is a part of bigger area somehow? So the water will mix with the Red Sea water, or they just want to close it as in
No,
Venice
they
would
want
do?
to add. I mean, what I have heard, they want to put as much species as possible to preserve for the next generation.
Maybe this should be combined with the first picture of your seminar, which are these barriers in Venice, actually. That
Yeah, exactly. But that is very warm in Venice.
Last chance for a comment.
I just would like to follow up on the historical perspective. We know that temperatures changed over several, eras in Earth's history. So you made that comment already, that we should look into records, historical records, to try and confirm some of these points. Yeah.
Mm-hmm. Yeah.
Thank you.
I see no further comments, questions. So Giacomo, thank you very much once more.
Thank you for you. It's a pleasure. Thank you.